My name is Don Welch, and in this video we're going to talk about using a digital accumeasure to measure the thickness of non-conductive targets. Here we have a sample of some closed cell foam that we're going to measure the thickness of. And we're going to talk about how to set up to do that and how to calibrate the digital accumeasure. So the first thing I'd like to talk about is what equipment we need to make these measurements. So what we're going to need is something to hold the probe, and here we have a fixture. This is an adjustable arm that's holding a probe. And capacitance probes that we're using to make this measurement. This is an example of the probe, and this is being held by the fixture right here, and we have a little micrometer that's used to adjust the height, and we'll talk about why we want to do that in a minute. The other important thing is we need a ground plate. So when we want to measure non-conductive materials, we're making the measurement by putting an electric field between the probe face and this ground plate, and then we're going to be sticking the material in between the two. So in this plate here you can see there's little tiny holes in here, and we've adjusted the probe so that no hole is underneath it. So you would need a flat metal ground plate, and you can see a wire here in the background, and this wire is used to ground the plate back to the digital accumeasure, which is an amplifier. And we also have a program that we're running on a laptop, and that program is going to be used to make the thickness measurement and to perform the calibration. So we're going to start by clicking on AccuMeasure Measurements program, which you see right here, and there's a number of tiles that come up on here that allow us to choose the measurement. So I'm clicking on the measurement tab here, and we're going to go back and take a look at this screen here. And in this tile right here, we have a picture of a probe over a non-conductive or dielectric material. Non-conductive materials are called dielectric materials in electrical terminology because they're not conductors, they're insulators. And then we have a picture of the ground plate here. So what we would do is we would click on that, and then that brings us over to the measurement screen. And before we do any measurements, we're going to have to calibrate this. So what I've done is I've cut out a sample, or a test coupon, if you will, of this non-conductive material. And we're going to use a caliper here to measure the thickness of it. So we either have to know the thickness ahead of time or the dielectric constant. Well, most people don't know the dielectric constants. And we're going to check the thickness of this and then put that in. But before we do that, I wanted to talk a little bit about the non-conductive materials, and this is one of them right here. And the non-conductive materials, there's some do's and don'ts with these. Number one, they can't have holes in them. They can't be wet. So you can't have this thing like in a process where it's soaking wet or soaked with any kind of highly conductive material. And water is actually, believe it or not, highly conductive. It has a dielectric constant of 80, which makes it almost like a conductor. We all know that if you're standing in water and you touch an electrical socket, you're going to get killed, and that's because it's mostly conductive. The other thing is it should be a homogeneous material. So the dielectric constant or the makeup needs to be consistent. It can't be a striation of different materials. If you think about something like a conglomerate material, maybe perhaps pressboard or something like that, where you have different thicknesses, different densities of materials that are pressed together. For example, like epoxies and wood and things like that. That's not a good idea for measuring the thickness of something like that. You'd have to use lasers for something like that. The other thing is that we don't want paper backing on these things either. This does have a backing on it. It's probably kind of a polyethylene backing, which acts as a substrate when they make this stuff to hold the material. So as they're pouring the goop on here before it dries, that keeps it from falling down into the web. So no paper backing. Why? Because paper is pretty porous and it can absorb humidity out of the atmosphere, And we talked about water having a high dielectric constant, almost being a conductor. So paper backings absorb moisture and therefore are not good materials, not good insulative materials to make measurements on. That being said, so we have two examples we're going to work with here today. We have this one here, which is a closed cell foam, and then I have another type of material we're also going to take a look at, which is a polyethylene substrate. This is a engineering material. I don't know exactly what it's used for. There's a number of things these could be used in, but you may need to know the thickness of these things consistently. Also, you can measure clear plastics and such like that. So to get started here, what we're going to do is we're going to go into the calibration program to set this up, and it's quite easy to do this. Once you get the hang of it, you can do it in less than a minute. So we set our probe height above the ground plate. This probe is a ASP 1250M. What does that mean? It means it's 1.25 millimeters measuring distance, but we also have range extensions on the amplifier. In this case, it's got a 3 times range extension, which gives us out to about 3.5 millimeters measuring range with this probe. And when we go into the measurements tab here, set up channel 1, that brings us into our calibration menu. And what we want to do is we want to set our probe, and that's why I have the vernier caliper here, so I can set the height at close to the maximum range. And I have it set right now for 3.1 millimeters. And it can go up as high as 3.5, but we don't need that. This foam here is about 1.5 millimeters thick, so that's plenty far away. So the next thing we're going to do is we're going to measure this guy. And we see that it's a little flexible, so as I'm pushing on the micrometer adjustment here, if I relax it, it comes out to 62 thousandths of an inch, or 62 mils. So we're going to put that under the probe, but before we do that, I'm just going to change the engineering units here from microns to mils, or thousandths of an inch. So I've got that set in here right now, and then we go back to our measurements tab and set up channel 1. And we check and see our gap is at 123 mils, which is close to 3 millimeters. Then for the next step, we want to calibrate the gap with nothing in there, okay? So it's just the probe looking at the bare metal. We could do a two-step calibration with two different types of material, but in this case, we're just going to do it with one to show you how easy it can be done. So nothing's in the gap. I'm going to enter 0 here, and I hit calibrate. It takes a few seconds for the probe to read it. It averages it a number of times, and that's entered. Now the next thing we're going to do is we measured this guy here, and we know he's 61 thousandths of an inch. I'm going to slide this under the probe, so our test coupon. Then I'm going to tell the system that this sample is 61 thousandths of an inch, and I hit calibrate. All right, that's it for the calibration. We're all set to go. I hit OK here, and we can see on the test coupon we're reading 60.9. Now, if I was slide this out, we'll go back to 0 because there's nothing in the gap. Then we're going to take this big guy here, this big sample here. Be careful not to ram the probe because the edges of this are curled up a bit. Okay, we slide it under, and I'm going to set our display settings here for the measurement such that the minimum reading, let's put in 55 thousandths, 55 mils for the minimum, and the maximum we'll say 80 thousandths because we're not expecting a huge change here. We hit OK. That's going to set our scale factor for us. So now if I hit start monitor, this is kind of like an oscilloscope display or a real-time monitor. So as we start recording, you can see we have 61 thousandths of an inch showing there. And then I'm going to slide this sample across. Whoops, snagged it on my finger there. All right, and you can see where I snagged it on my finger and lifted it off. Now, you don't want your dielectric material to get too close to the probe face. as long as you're about a quarter of the distance away from the probe face, your readings will be good. So what we're doing is I'm sliding it back and forth, all right, and we're reading the 61 mils, and we're seeing a couple of bumps in here. Well, as this material is formed, there are ripples that are in it, and you will see those ripples, and those ripples are actually quite tiny. It looked like a big bump. There, I can stop the display. It looked like a big bump there, but in fact, it's actually only about another 1 or 2 thousandths of an inch. So these very small changes in the material will show up as fairly large changes on your graphics display here. And you can also log this information too. So we can keep track of our in-process thickness measurements. And the other thing we can do too is, and I'm just gonna show you the screen here. We have limit alarms. So I can actually go in and I can set up an over limit alarm, which will allow the computer to talk to another board that has a relay on it, so you can have an alarm indication. Let's say you anything over 65 thousandths of an inch, you want a red light to turn on or an alarm bell to ring. We would set those alarm functions up in this display right here. So you can be data logging and also have audible or a lamp indication that your process is getting out of the limits that you have set for it. And that's pretty much it. Next, we're going to set up and take a look at the polyethylene material.